Alright, so with this video, I'm going to go ahead and work one of the two challenges I gave you in class last time, which is using calculus of variations to calculate or find the function which satisfies the shortest distance between 2 points in flat space. Okay, very basic use of this technique. But we're going to build on it for more and more complicated things. For instance, the second challenge I gave you was the brachistochrone problem. Going from A to B under the influence of gravity, calculate the path which minimizes the time it takes to go from A to B. That's a more complicated problem, but it uses the same technique. So, here we go. We have, let's say, 2 points A and B, and I'd like to discover how can I get from A to B going the shortest distance. Now, of course, we know the answer to this in flat space for sure is a straight line, right? Just go straight from A to B. That's not very straight. That's about as straight as my hand can get. But I want to prove it. Let's prove it mathematically. Now, how would we do it? We're going to use the calculus of variations, and that is to say what we'd like to do if we want to know what is the distance from A to B. Well, we are going to integrate from A to B the little differential distance. Now, I know ds is the square root of x squared, dx squared. Let me go ahead and rewrite that. Dx squared plus dy squared. That's Pythagorean theorem, basically. But generalized in higher dimensions, this is still true. You just tack on the extra spatial dimensions the same way. But what the heck does it mean to do the integral of this thing? Dx squared plus dy squared. First of all, what's the integral with respect to? And even if it's with respect to dx or dy, it's inside of a square root. How do I handle something like this? Well, we do a little trick. And what we do is we say, okay, this is the same as saying dx squared times 1 plus dy squared over dx squared. Right, all I did was factor out a dx squared, which put an extra dx squared under the dy squared. Then I'm going to say let dy by dx be called y prime, just as a simple shorthand notation. Well, if I do that, I can now take the dx squared out of the square root as a dx, and what's left inside is 1 plus y prime squared dx from A to B. And now what calculus of variations says is that, first of all, this integral would tell me the distance going from A to B. Well, if I want to find the shortest distance, then what I should do is minimize this function. And the way we're going to do it is we're going to take this inside piece here, we're going to call that f, and we're going to use the Euler Lagrange equation and see where it leads. So let's do that. First of all, we have our f was the square root of 1 plus y prime squared. And the Euler Lagrange equations says df dy minus d by dx of df dy prime is equal to 0 if we minimize this, our original integral. And most of these are partial derivatives, so it explicitly has to show the dependence. So for instance, for df dy, that y prime sitting there doesn't count. That's y prime, it's not y. Now, of course, the d by dx in front of the, what is this? In front of the second term, that is a total derivative, but we'll get to it. So let's go ahead and apply our function into these Euler-Lagrange equations and see what we get. Well, first of all, this first term is 0 because there is no y dependence, no explicit y dependence. So we get minus d by dx of the partial of, with respect to y prime, of square root, or in fact, let's just do it 1 plus y prime squared to the 1/2. And this is equal to 0. Well, the minus can go away, or we could leave it. Let's see what happens. Minus d by dx of the partial of this stuff in the parentheses. Well, first of all, we get a 1/2. Then we get that thing, 1 plus y prime squared to the minus 1/2. And then we got to differentiate the inside, and that gives us a 2y prime. And all of this is equal to 0. Well, the minus now can go away, so we get d by dx. The 1/2 will cancel the 2 here, and it's y prime over 1 plus y prime squared, square root, equals 0. All right, well, if the derivative of this thing is equal to 0, that means that thing better be equal to a constant, right? Because the derivative of a constant is 0. So this says that y prime over square root of 1 plus y prime squared must be equal to some constant. I'll call it alpha for now. Now we're going to rearrange some stuff. So we get y prime equals alpha square root. And now I want to get rid of the square root, so I'm going to square both sides. So I get y prime squared equals alpha squared times 1 plus y prime squared. Now, let me go ahead and collect the y primes on one side, everything else on the other. So this becomes y prime squared minus alpha squared y prime squared equals alpha squared. Right? All I did was distribute the alpha squared in, then I brought the y prime term to the other side. Now let me factor out y prime squared. 1 minus alpha squared equals alpha squared. Okay. Now let me rewrite it on the next page so I get some more room. Y prime squared times 1 minus alpha squared equals alpha squared. All right, let me divide the 1 minus alpha squared over. So I get y prime squared equals alpha squared over 1 minus alpha squared. Let me take the square root of both sides. So I get y prime is equal to square root of alpha squared over 1 minus alpha squared. And I'm going to go ahead and just call this thing, I don't know, m, let's say. All right, now what? Well, what was y prime? If you remember, y prime is, dy dx from the beginning equals m. Let me move the dx over, so I get dy is equal to m dx. Let me integrate both sides. So I'll get a y on the left, and on the right I'll get an m times x plus a constant of integration. And that constant of integration, let me call it b. And now we see, indeed, our function y, the path that we're going to take is given by this particular equation, mx plus b. And we know from math that y equals mx plus b is indeed the equation for a line, a straight line. So there you go. Very interesting. We've just proved something we all take for granted. The shortest distance between 2 points in flat space is a straight line. We proved it using this very fancy technique. How did we do it? Well, first thing we need to do is we need to calculate what is the distance from A to B for any path we may choose, any random path, whatever it might be. And then what we're going to do, so that's integrating ds, where s, of course, is the distance. So integrating ds will give us the total distance from A to B on what other path we're about to take. Well, what is ds? ds from this Pythagorean theorem-like thing. We fancy it up a little bit. We factor out a dx, and now we have an integral we can work with. But what we actually are trying to do is not integrate this, but rather we're trying to minimize this because we want the minimum distance to go from A to B. And to do it, we take the integrand, the thing inside the integral, and we apply it to the Euler-Lagrange equations. And once we do that, we go through, we simplify, we do a bunch of algebra, cleaning things up until we finally get down to the final answer. And the final answer tells us that the shortest distance, the path, which gives us the shortest distance between A and B, and by the way, this little b is not that other capital B, the point B, but the path, which gives us the shortest distance, happens to be governed by the equation of a straight line. Now, for other problems, like I said, the brachistochrone problem, that's this one here, some A here, some B here, and now let's say a marble is going to roll down a hill or some kind of a platform under only the influence of gravity, no air resistance or friction or anything like that, so only gravity is going to let it move. And we want to know what is the path this marble should take, or that is to say, what should the shape of the floor be so that it takes the least amount of time for this marble to get from A to B. And it turns out it's not the straight line path, and there is a shortest time path. That's another thing that may not necessarily be clear, because if you think about conservation of energy, we know that the path doesn't matter when we're calculating something like the final velocity. If we go from A to B under conservation of energy, as long as you can actually get to B, then it turns out the shape of the hill doesn't matter at all. Once you get to B, no matter how you got there, you're going the same speed. However, that does not mean that by the time you get to B, it took the same amount of time. And so how would we work a problem like this? Exactly the same way. This time, we're going to integrate dt. What is dt? Well, we know v is x over t, right? So dt is going to be dx over v. And so it's this thing that we're going to stick into our original integral instead of ds. I'm sorry, not dx. Obviously, it should be ds, because it's not one dimension. ds over v. Well, we already know what ds is. That's what we did here in this one. But now we have an extra v. And so we stick with that v as into the integral. We have our ds. Now we know our function f for that problem. We apply it to the Euler-Lagrange equations. We do the derivative, set it equal to 0. But then, what makes this one a little bit harder, this brachistochrone problem, is some of the fancy algebra, fancy substitutions you might have to do in order to get a result that's meaningful to you. So, for the shortest distance problem, the result just popped out at the end. Y equals mx plus b, very clear to see it. For brachistochrone, you're going to get parameterized equations, parametric equations, and you have to do some fancy substitution, but at the very least, you should be able to handle finding the function that needs to be minimized, sticking it into the Euler-Lagrange equations, and simplifying as far as you can go. So, next time in class, I'm going to go ahead and do the brachistochrone problem myself, And then once that's done, we have enough examples, enough practice, we'll start working actual Lagrangian mechanics type problems, things like, here's a pendulum, and it's swinging back and forth. I want to know the equation of motion for the pendulum. Or maybe we have a spring harmonic oscillator system, and it's going to oscillate back and forth, and I want to know what's the equation of motion for this. And a whole bunch of other physics problems, and we're going to use Euler-Lagrange equations to do it. All right, so I hope this was helpful. I will see you next time.